So this week we're going to talk more. We talked about temperatures now, and we've talked about pressure. Well, we're going to delve in a little bit about wind. And I just wanted to quickly start off by just showing some winds. We can look here, low pressure up here, right off of western Ohio. Notice the winds around it. We said that winds around low pressure flow counterclockwise. Well, here we have northeast winds, continued northeast. Here we have northwest. Here we have southwest. And here we have east. Very good conclusion for that one. Works just great. We have nice counterclockwise circulation around this low right here. What other things I just wanted you to know, look at a little bit. Look at the winds over the water. They tend to be more, even though they're not a lot anywhere, than they over land. There's a little stronger wind over the water than there over land. Let's see if we can explain that as well. And also we talk about convergence and look at the winds blowing into this front and parallel or even into it from the other side. So winds converging there. This is all at the surface. There's lots of things that go into why these winds occur. If you look a little bit aloft, this is actually at 500 millibars. Notice contours. 500 millibars are all contours. So this is the height of the 500 millibar surface. And notice the winds kind of flow right with the 500 millibar surface. Yes, they go around this low, but they're flowing right along with the contours again. The same over here. And they're also stronger than at the surface. So, questions to ask here when we're learning about wind. First, you want to know what it is, and then why this difference. Why is the wind stronger up at 500 millibars? Also, why does it blow with the contours instead of against it like the surface did? And maybe why is the wind counterclockwise around the low and clockwise around the high? So let's go take a look at some stuff here for a minute and see if we can learn a little bit about why this is. So we're going to start. Very first thing is learning just what wind is. So what forces control it, and what causes it to have the different speeds and direction. A number of years ago, there was a song written about the Edmund Fitzgerald, one of the largest ore carriers on the Great Lakes, and in 1975, it sunk. Winds were estimated at 60 miles per hour. Waves are 12 to 16 feet high. So why were the winds, example, why were they high? So winds are just the locomotion of air. In other words, if you walked outside and saw a blade of grass moving in a direction, or leaves coming down from trees, dust moving in the air, you can see how the air is moving. You can actually feel it on your body. That is wind. In other words, wind is invisible. There's nothing in the air except when you feel it pushing on you. So what causes wind? We learned a little bit about force when we talked about pressure. Well, force is what actually causes wind. It's a push or a pull that causes an object to move from rest. Newton just said it. He is the man that came up with most of these equations, and he said that mass times acceleration is force. Again, mass is how many molecules we have in a given area times the acceleration of those molecules, how fast they're picking up speed. So we're going to apply this to air parcels now. And here is a list of the forces that typically impact air parcels. We have pressure gradient, centripetal, Coriolis effect, friction, and gravity. So let's start with pressure gradient. We learned some things about pressure in the previous chapter and video. So we know that pressure wants to be equal everywhere. That's the first thing it does. So if I have high pressure the air is always going to blow from high to low pressure because it wants to equalize that. So high pressure has more volume of air, low pressure has less volume of air. So for both, the wind is going to try to go from that bigger volume of air to the smaller one. Pressure. That's the pressure gradient force. Now, the closer together the isobars are, the stronger that wind's going to be because it's like a steeper slope. So when the isobars are pretty far apart, like they are right now, there are not very many isobars out there. It's going to be kind of light winds. So that is, interestingly, the vertical pressure gradient, we talked about this, is significantly more than the horizontal. So you would think, wow, wind would really blow in the vertical. Well, it doesn't. There's a reason for that. We'll talk about that. So here you can see a perfect example. The closer the isobars are together, the stronger the wind. And again, blowing from high pressure to low pressure. Same here, weaker winds. So air is always going to be doing this, and it's always going to be perpendicular to those isobars. The same holds in the upper atmosphere where it's contours. That literally is a pressure gradient because the higher the contours are, they're going to want to slope down to the lower surface. The winds are going to blow from the higher surface towards the lower surface. The next force, centripetal or centripetal. You'll notice that isobars curve on a weather map around low pressure, around high pressure. They curve up in the upper atmosphere as well. And let's just think about this simpler even. When you drive around a corner, or as in this case, you spin a ball around in the circle, what is keeping that ball on that circle? What is holding it there? Well, what's holding it there is centripetal force. That force is working back away from the ball to the object it's attached to. So if the winds are blowing around low pressure, around high pressure, there's a force that's working with that, that's counteracting the pressure gradient force, causing those balls or wind to move in a circle. So anytime you have a curved motion, you have centripetal force. It's not independent. In other words, if I got rid of that force, the ball would tend to go straight. All right, Coriolis effect. This is unique to a rotating planet, we'll say. So the Earth spins, rotates around its axis. Because of that, when you look from above, the top of the Earth or the bottom of the Earth is not moving as fast as the middle. This creates a force called Coriolis effect. You can actually think about it with this way. Here's 100 degrees west, right there at 40 degrees. If you go a few hours later, hardly any motion at the top, right? But this has moved significantly to the right. That motion is what we call a Coriolis effect. In the northern hemisphere, it acts to the right of the wind, of the other forces. So in other words, if air was moving from west to east, the Coriolis effect would tend to want to make it turn towards the southeast. It would be pushing away to the right. And here you can see all these deflections and all. The strongest deflection is up closer to the North Pole. The weakest down by the equator. Matter of fact, the equator has no deflection. Southern hemisphere, they just do the opposite. So the next force we're going to talk about is friction. If I am moving something over a very bumpy surface, say you were pushing an object along the ground and all of a sudden there was a bunch of bumps there. That object is going to be a lot harder to push over those bumps than it is if the ground's all flat. Well, air works the same way. More bumps, the more friction is caused. This friction can be in terms of molecular viscosity or eddy viscosity. Eddy happens in fluids. If you ever look at your cup of coffee in the morning when you drop creamer in it, we'll say, what happens to that creamer? It goes in all kinds of different directions. That's eddy viscosity. That is turbulence. You can see here friction along a water path bubbling up, or a fence holding snow, slowing down the wind, letting the snow deposit there. We see snow fences in the wintertime in a lot of different areas where there is significant snowfall. The final force is gravity. Gravity always acts towards the center of the earth, so it doesn't impact directly horizontal motion. It's all up in the vertical or down towards the ground. But it will always pull an object down towards Earth. So when you're looking at gravity, gravity is always working in that direction. Now, knowing we have gravity and all these different forces, and knowing some other things here with the first law of motion, which when the air is all balanced, the net acceleration will be 0, we came up with some simple equations and we named them. One of the simplest is hydrostatic equilibrium. Another one's geostrophic wind, gradient wind, and surface winds. So we're going to take a look at these forces and say how they interact to create this. All right. Because we know the pressure gradient is very, very strong in the vertical, you would think that, with that, all objects, all the gases in the atmosphere would just go flying out into space. Well, they don't. The reason for that is all because of gravity. And because of that, what we call this hydrostatic equilibrium, gravity balances the vertical pressure gradient force. That is the hydrostatic equilibrium. So if you looked at a little parcel of air, we would say, the pressure gradient is pushing it up, and gravity is pulling it down. It's balanced, it's not moving. Now, doesn't mean air can't move. Air can go up over a mountain or over a front and begin to move up. It just says it will not accelerate. It will move at a constant velocity. That's all the hydrostatic equation is saying. Now we're going to get into a geostrophic wind. I showed you at the very beginning winds parallel to the 500 millibar contours. They do that because of the geostrophic wind. Geostrophic wind is a balance between the pressure gradient and Coriolis effect. With time, the pressure gradient is going to accelerate an air parcel. And eventually that acceleration is caused to move at a speed that's enough, because as you accelerate an air parcel, the Coriolis effect increases and they eventually balance. When they become exactly equal, they move parallel to the contours or isobars. And that is the geostrophic wind. Two forces only, pressure gradient, Coriolis. Now, when we're moving in a circle, because the objects are constantly changing direction, these forces are not balanced. And there's an extra force called the centripetal force. When that happens, objects move in a circle, because now you have pressure gradient, Coriolis effect, and centripetal force all working together to cause the objects to move in the circle. Finally, when you get down close to Earth, we have a lot more friction. What this does is slow the wind down. So you have the pressure gradient and we have the Coriolis effect. Normally, they would be balanced if everything was moving. However, friction has slowed that wind down. They're not balanced. So now that object is moving to the right, and we wind up with winds blowing toward lower pressure at an angle and away from high pressure. So there are three forces here: the pressure gradient, the Coriolis, and friction. Friction slows the wind, so the pressure Coriolis effect is not as great, allowing this to occur. So with that, above the boundary layer, so above where friction is greatest, we get more of the geostrophic wind. Down below that, we have more of the impact of horizontal winds impacted with friction. And that is why winds tend to blow into low pressure and out of high pressure. So if they're blowing towards something, we know we have winds converging. If you're blowing out of something, you have winds diverging. We learned last time that when we have one impact at the bottom of the atmosphere, there's a opposite impact at the top. So if I have converging winds into low pressure, that means air is going to be forced to rise and the air atop is going to be divergent. And here you can see that. So finally, we're going to talk a little bit about winds over water and this friction. We all, if you lived along Lake Erie or along a coastline, like in Florida or along the East Coast, you're going to get a breeze coming from the water and towards the water, depending on the time of day. So with that, winds over the water are always going to be stronger than the winds over the land. So if I have a sea breeze during the daytime moving from the lake or the ocean towards the land, that air is going to be moving faster than when it reaches the land. So as the wind approaches, that air approaches the land, it's going to slow. When that happens, you have convergence, which causes the air to rise. That's why you see the clouds and some thunderstorms and all along the sea breeze front, because of that slowing motion. It's also why you have lake effect in the wintertime. Some ways of measuring wind are, we have a wind vane, and here's a table that Beaufort scale estimate of wind speeds based on leaf motion, smoke moving. And there's a different types of anemometers. And remember, all of this we include with wind is wind direction, wind speed. We want to know both. So it's always going to be that, not just, oh, the wind's 55 miles an hour. I want to know where it's coming from. Finally, there's a quick little estimate on scales of planetary motion in this chapter. We're going to go into a lot more detail of that in another week or so. So I think that's about it. Let me know if you have any questions with this.